All right, so we have two great presentations in this session. They were both remote speakers, so I'll introduce our first one. I'm pleased to introduce Yolanda Gill. She's the Director of AI and Data Science Initiatives and a research professor at the Information Sciences Institute at the University of Southern California. She's a fellow at ISI. She's also a research professor in computer science and spatial sciences. She received her MS and PhD from Carnegie Mellon with a focus on artificial intelligence and cognitive science. Dr. Gill collaborates with scientists in many domains on semantic workflows and metadata capture, social knowledge collection, provenance and trust, task-centered collaboration, and automated discovery. In 2019, she chaired the CRA AAAI 20-year Artificial Intelligence Research Roadmap for the U.S. with key strategic recommendations based on extensive community contributions. She initiated and led the W3C provenance group that led to a widely used standard that provides the foundations for trust on the web. She's a fellow of the Association for Computing Machinery, the Association for the Advancement of Science, the Institute of Electrical and Electronics Engineers, and the Cognitive Science Society. She's also a fellow of the Association for the Advancement of Artificial Intelligence and served as its 24th president. Dr. Gill was the first computer scientist to receive the Geological Society of America Emily Allison Award for outstanding contributions to geoinformatics and data science. She serves as co-chair of the Stanford AI Index. In 2024, Dr. Gill was appointed to the National Science Board for a 6-year term by President Joe Biden. Dr. Gill's research focuses on artificial intelligence and particularly on intelligent systems for knowledge capture and discovery, where she investigates a variety of projects concerning scientific discovery, collaborative planning, and problem solving, and information analysis and assessment of trust. She collaborates with scientists in many domains on semantic workflows, metadata capture, provenance and trust, social knowledge collection, task-centered collaboration, reproducibility, and automated discovery. All right. Dr. Gill.
Thank you very much. I'm very sorry not to be there. It's always fun and exciting to be in Colorado, particularly around your campus. So my apologies for not being able to be there, and to be able to also learn more about data science and AI from all of you. I want to share with you today all the excitement that I have about AI challenges and opportunities. I have been involved with AI for decades, and it gets more and more exciting every year. So I want to share my reasons for that excitement with you. I was involved with the community roadmap for AI for the next 20 years, and we did this exercise in 2019. So this was, the transformers had yet come out, and it was, before all the generative AI revolution. But 5 years later, this community roadmap still stands very much so. And I want to share a little bit about the research areas that appeared there, because these are areas that I think still stand in the way of AI progress. So in this community roadmap, we had many workshops and discussions with thought leaders in AI and computer science and beyond. And we looked very closely about areas of research that are more societal drivers for AI. And the report had many scenarios of how AI research could result in changing the lives of individuals. So from evidence-driven policy to healthcare, to education, to innovation and business opportunities, to accelerating science. I think we saw many opportunities for that. And the technical areas that the roadmap outlines, I wanted to share with you because I find a lot of interest in large language models and generative AI, but there's many areas of AI that we cannot neglect and are very important for our success in addressing challenging problems of our time. So one is integrated intelligence. We still don't have a very good approach to a system of systems science for intelligent capabilities. So this would mean that we can take a model of language, a model of autonomy, and kind of integrate them together. And we don't have a very good sense of how to do that kind of modular integration of AI capabilities. And so we have much work to do in that respect. And I think that this will result in major advances. And I'll talk a little bit about my own work in a bit, and just to share what we're doing in this respect in my research group. The second big area of this AI community roadmap for research in the next 20 years was meaningful interaction. So here we have come a very long way. One of the challenges in that area was natural interaction, and I think we're seeing that. But what we meant by meaningful interaction was that you could actually trust the AI that you're communicating with, and that you could delegate tasks or coordinate tasks with an AI to accomplish something bigger than what you can accomplish on your own. And I think that we're still pretty far from that goal, and much needs to be done in terms of making AI systems helpful collaborators and helpful to delegate tasks to. The third area that I think is still very much open is what we were calling self-aware learning. So this means systems that are able to learn from data, but also be able to learn from other methods, from being taught, from listening, from asking questions, and to be self-aware of what they don't know enough about, or when their knowledge becomes obsolete, or when they need to expand their scope of knowledge and seek the means necessary to learn about that new topic. And I think that we are still far from having these entrepreneurial learning systems that we were envisioning in 2019. So there's much work to be done in AI to really have strong and meaningful impact in many areas that society cares about. Many of these areas we need really capable academic researchers to undertake and to push forward. So I encourage you all to not lose sight of these big AI problems. One of the things that we recommended in this roadmap was not just investments in certain research areas, but also investing in national AI infrastructure. And I think that that is making a lot of difference in many ways, and I want to talk a little bit about that. The third area we talked about was workforce training, and maybe that's a topic for another day. But I want to talk about the AI infrastructure and the efforts that are ongoing that are significant. I want to say that in terms of national AI infrastructure, we have seen NSF respond to the recommendations of this report in terms of creating national level AI research centers, and we've seen the AI Research Institutes program. We also recommended mission-driven AI centers, meaning that they were targeting particular societal drivers and were providers of AI-ready data and an environment where testbeds and useful capabilities could be investigated and advanced. And we've seen the recent call at NSF to create AI-ready testbeds and the plans for that. The third area that we recommended was creating open AI platforms and resources. And there's been a lot of activities from a national level task force that the White House started 3 years ago for a National AI Research Resource, or NARE. So the White House task force actually produced a report that made recommendations for the implementation of these national AI resources for AI. I want to talk more about a workshop that we had at NSF in last May, about the needs of the AI research community in terms of data, compute, but also other resource needs that may give you ideas of where to contribute in terms of building this national resource. So one thing that this workshop identified were prototypical AI workflows that have immediate resource needs, particularly compute, but also data and also human support, human effort to support these large computations. So from machine learning, lots of work on exploring new architectures and new algorithms, to using larger scale data sets, to applying a well-known method to a new type of data or data with different degrees of quality, to comparing and improving on different approaches. Generative AI in particular, as we know from recent years, has very high demand for compute resources, and in particular for training or pre-training large models, for compressing foundation models, for analyzing existing models in terms of bias and other characteristics, on querying models and provoking inferences that require computation, to including structured knowledge and other knowledge sources into existing models, to including agent tasking combined with model prompting. So all of these also coming from generative AI that is very much of interest to the AI research community. And, if we had more resources for AI, generative AI would advance, but also I think from the academic community, we would see a lot more exploration on the design of AI systems and what that design space might look like, on the foundations of generative AI that may lead to new ideas and new architectures, to how to incorporate large amounts of reliable knowledge for reasoning and for learning, how to understand human intelligence, accelerating science, and really transforming all areas of human endeavor that we just discussed in the context of that 20-year community roadmap, if we're able to reach scale. Let me tell you a little bit about resources for future AI research. And the workshop report has a lot of details. I want to highlight here the ones where I think people don't think about enough, and I wanted to highlight those because to me these are important and present interesting opportunities. So in terms of compute resources, of course, GPUs and a different way to allocate compute cycles. One of the things that we learned is that AI research is very different from the kinds of computational science that is traditionally using high performance computing and supercomputing resources. So what you see in computational science is you want to simulate an earthquake, and so you have the wave propagation software, and you want to run the same software many times from different fault rupture assumptions and different kind of parameters, but you're running the exact computation many times, and you just need to run all of that compute. In terms of AI, it's very different. So we do a lot more exploration and experimentation. You may run a few runs and completely change your mind about the potential for that particular experiment to succeed. So you want to interrupt that line of inquiry as early as possible and be able to redirect your experimentation somewhere else. And so traditionally, high performance computing, for example, the National traditional access infrastructure, you would submit a plan for how many computations, what is it going to look like, the software that you're going to run, and exactly what is the endpoint. For AI, when you request compute cycles, there has to be a lot more flexibility for that built-in experimentation. In addition, the high performance computing expertise has to be accessible and connected with the researchers and the students. So as we run large AI models and large AI computations, there's many challenges, lots of failures from hardware to networking to software to memory, bugs, incompatibilities in libraries. So people are a very important component, and their expertise is a very important component for this. We talked about quantum as well, and just this idea of not waiting for quantum to be able to accommodate all computations, but to be able to have hybrid architectures that have some quantum aspects of quantum computing and other aspects of more traditional computing. In terms of data, of course, we want to share data and do better tools for data integration, maybe using AI for data integration. But we need a better kind of governance for sharing data across institutions. So thinking about, for example, education data or health data in particular, and how each university and institute collects data. They have their own protections for the data, and we need to figure out a governance structure where we can do agreements to share data about certain cognitive decline or other kinds of neurological disease, and be able to have those agreements be very seamless and very ready to happen. Right now, they take months, if not years. We also need to think of data in terms of synthetic data and simulation data and be able to be ready to share those as well. We see a lot less sharing of the data that's not collected from the physical and the virtual world. In terms of software, also this challenge of combining a very complex software stack for AI that includes the latest libraries. So that's another difference from more traditional computational science, where the AI software stacks are very dynamic and need to be updated constantly. So if you use the latest version, there may be incompatibilities and bugs, and we really need a much more advanced way to deal with software stacks than we have seen in the past. So you see that some of these topics require some careful thought, and in other cases, new research across the gamut of computer science and beyond. In terms of AI models, you won't be surprised to hear that we wanted to have open community models, not just open weight and not just open software, but really open methods, open workflows, open discussion of what experiments failed and didn't take us anywhere. So we need a lot more openness in terms of how models are built. And also this idea of pushing for federated models that can be built in a distributed fashion, and then together they understand better a more global phenomenon. So this is particularly beneficial for health, where the data might stay in place and then models are built locally. But when the local models are shared into a federated model, the quality improves significantly than any of the individual sites. And then there's a lot of other aspects of managing AI workflows, considering them scientific assets, something that's worth collecting, sharing, learning from, redesigning, improving, optimizing, etc. Being able to offer test beds that are for evaluation, not just the classic benchmarks that we see in AI, but also test beds that may include dynamic or interactive components, and real-world test beds as well. Education was considered very important, and there needs to be resources to be able to train people on AI skills and on engage in flexible careers, in particular to have industry experts come to academia or government, both in the middle of their careers. And finally, there's also a great need in AI to look at AI systems and evaluate AI systems and run large computations for more interactive AI systems, as well as AI systems that are more embedded into robotics or cyber physical systems or sensors, Internet of Things, etc. So these are kind of new resources that one may not think about. So computation, of course, is key, but when you think about NAIR and when you think about a national AI research resource, we have needs for these many other topics and areas. And I hope that everyone in this meeting will be contributing to this national need and in terms of any of these dimensions of the resources. I want to spend a little bit of time talking about my own research, and I'll do this very quickly because most of the talk I wanted to focus on national needs and really the big picture about AI and national resources. But I want to talk a little bit about what drives me and what I find interesting and important in terms of AI research. So one of the things that we focus on is this area of modeling human natural systems. And that includes ways to understand droughts and floods that lead to food insecurity, or droughts that lead to limited availability of certain resources. Also, international conflict is a result of these limited resources. Wildfires, flooding, there's many areas where we see this connection between human and natural systems. So usually when you build models of how climate or hydrology or agriculture works, they are vertical models that are very focused on that one particular area. And what we find is that the big challenge is to connect all of these different models, not just on the natural processes side, climate, hydrology, agriculture, but also on the human side, the economic models that are necessary to understand the impact on food availability, for example, or the impact of snow melt on local economies. So one thing that we pay particular attention to is not so much understanding the science and advancing the science of a particular modeling area, but really connecting that science with policy and decision making. And in particular, we pay attention to interventions. So what interventions can we study and analyze using science models that would help human decision makers eliminate or mitigate undesirable situations? So for example, if you increase fertilizer subsidies that the government provides, that would increase crop production because farmers are more likely to grow more crops more often and also harder to grow crops. Or carrying out controlled fires in a region so that there's not so much brush, so that when there's a mega fire, it can only expand so fast. And there's a lot of these controlled burns that can really prevent mega fires. So interventions are things that we can recommend in terms of decision making. And one of the things that we've learned is that if you study these models in verticals, you can generate a lot of recommendations. So these are examples from the Ethiopian food insecurity area. And they have many recommendations, but they're very vertically minded. So they'll look at one aspect and recommend one intervention. But one does not know what side effects or what other effects that particular intervention may have on the rest of this complex human natural system. So it's very necessary to connect all of these models and to understand them together to recommend the interventions. So in our research, we've worked on model and data integration so that we can recommend science-grade models to guide decisions and to explore potential interventions. This requires a lot of work on the modeler side. So we work a lot with scientists to re-engineer their models so that they expose interventions and results that may come from them. We use a lot of knowledge technologies, knowledge graphs, ontologies in particular, to do this. But this is a picture of a process where you come from the science side that tells you what models may be possible with the data that you have in the region that you're trying to study. But then there's also these demands from the decision-making side about what type of model is needed and what modeling capability might be needed. So these are very important consideration for us. So we've created this environment in this MINT framework to describe models that can calculate certain indices for climate, for food production that are important for decision making, then variables that are quantified indicators of how the system is producing food or having other aspects that are affected by other models, and then parameters where you can express interventions. We have created ontologies to describe models of physical systems, and they're pretty uniformly applicable to groundwater, hydrology, agriculture models that we've created. So we start always with the questions that decision makers have, the driving variables that they want to study, the response variables that they want to see come out of the simulations. When the question of interest is expressed, that means that only certain models can help address those questions. So not every hydrology model helps with the questions of interest for the decision maker. So we recommend models. We find data sets and adjust the models so that automatically we can set them up to study the questions of interest and run them. This means that we can look at indicators and indices. These are variables in the system or combinations of variables in the system that are generated by the models. The explanations for what came to in the analysis for recommending certain interventions. So this is very well connecting the science with the decision making. This is another example from planning controlled fires. These burn managers that you see on the left, they really don't understand science models. So our goal is to capture enough knowledge of what a scientist, a fire scientist would consider about that region, that area, and then use that knowledge to recommend to the burn managers the time frame, the extent, the approach to igniting the fire, and so on. So I'm going to end here and leave a few minutes for questions, if that's okay. What I tried to highlight to you is that there's many technical research areas in AI that we can address and that we can expand to really help us make profound changes in societal problems that we're not solving today with the current results that we have. So I mentioned integrating intelligent components and integrated intelligence architectures and a science of systems for AI. I mentioned meaningful interaction where we can delegate and responsibly count on AI to solve some tasks, and this idea of learning systems that are self-aware and can task themselves. And I gave you some examples of the work that we're doing to integrate different capabilities, to connect science models with decision making, and use knowledge as a bridge to integrate powerful capabilities from AI or otherwise. And I will stop here and take questions.
All right, thank you for the great talk. Are there any questions from the audience? Great.
Hi, thank you so much for talking. I had a quick question regarding one of the aspects for the community roadmap and one of the resources. You mentioned that sharing data among a lot of different communities and then also like interdisciplinary sharing of resources. How exactly does that process look? What do you think are roadmaps that can lead to the successful sharing of data given data's, inherent value? It's kind of becoming the gold of our generation. So how do you see that process going and what trends do you see happening and how can we work towards that?
Yeah, so you ask a very important question because we have come a long way in terms of sharing data within communities. So, for example, if you need climate data or if you need hydrology data, you will go to Quasi. If you need ocean data, you may go to Woods Hole to get that data. And communities have developed a lot of metadata standards, ways to describe data, ways to share data. There's this notion of fair data that I'm sure you all have heard about. But there's also this notion of repositories that follow TRUST principles, meaning that the data repositories will be there for the long run, that they commit to certain quality of service, etc. So we've come a long way in terms of sharing data within communities. But if you don't work in climate and you want access to certain climate data, you may not get a very good sense of, you may running across the repository where the data is. That takes some work. That should be much easier than it is today. But you go to that data and you don't have a very good sense of the relative quality of the data, how accurate it is when it makes predictions. So there's a long way that we need to go in terms of sharing data across disciplines. I think that NSF has funded supercomputing centers and national compute resources for a very long time. They have developed a governance. They have developed coalitions, advisory committees, managing committees, and policies that help each institution share resources. And I think we need to develop something like that for data as well. And the governance of data is a big topic for us in AI moving forward. Thank you for that question.
All right, thank you. Any other questions? Okay, so I've got a quick question. So I want to talk about kind of the national strategy that you outlined that you participate in developing with respect to changes at the national level currently. So to name a couple of things, the current administration rescinded the previous administration's executive order on AI safety and also announced a massive collaboration and investment in data centers with large tech companies. And so that kind of, and then coupled that with the changes in funding that are currently being played out, has shifted the balance towards very big tech companies who are already the drivers in the era of generative AI. So, what can universities and research institutes do to remain competitive and relevant in under this, under these changes where the the support from the federal government is maybe differently characterized, let's say, than it was previously when you developed the strategy?
Yeah, that's a very good question. Thank you. So first, I want to share that I am hopeful that we will see support from AI in this administration in ways that will be meaningful and impactful for academia. So, already in the previous Trump administration, we saw the creation of a national AI center and a lot of organizations in government that still remain today and have been operating for the last 6 years, managing AI in the government in different ways. And I believe that will continue moving forward. Biden's executive order was rescinded, and a new executive order was published. That is not uncommon of a new administration. But if you're interested, there were two memos that came out of the Office of Management and Budget just last week, last Monday, with provisions to mandate government to be bold in embracing AI for the government business while taking a careful measurement of any risk that AI applications may incur. And so having chief AI officers across all agencies within 60 days is one of the mandates of this executive order. Having aggressive plans to include AI in processes that could be streamlined, but analyzing the risks of any inclusion of AI, and also monitoring any deployments of AI systems that may become undesirable and immediately rescinding their operations. So in my brief summary, you can see that the undertones of safety and attention to risk that were present earlier remain. So I'm very hopeful in that sense. I also want to answer your question about industry. That's a very long answer that I could give, but I think this was my impetus for sharing with you what I said in today's talk, that there are many technical areas in AI that remain unsolved, that only the incredible creativity of students and academic pursuers of research topics can really tackle. These are very hard questions with no clear impact in a company's bottom line. And so I wanted to highlight those areas for you, as well as societal drivers that maybe we won't see industry undertake as goals. So I think when I talked about the NAIR and the resources needed, it's not just industry giving out computation cycles, but the previous question about the data governance and the data sharing challenges that we face. I think that only the ingenuity that we see in academic circles can address those problems.
All right, thank you.